Hi, I'm Ophelia. I'd like to tell you a little bit about Jupiter's aurora. Our ancestors have been marveling at the Earth's aurora for millennia. The oldest recording of an auroral sighting is thought to be a 32,000-year-old cave painting. They could never have imagined that the same phenomenon occurs many millions of kilometers away on 7 out of the 8 planets in our solar system, the exception being Mercury. How do we get these aurora? For the Earth, it all starts off with the Sun. The Sun releases a constant stream of charged particles called the solar wind. As the solar wind flows out to the edge of the solar system, they can meet obstacles like the Earth's magnetic field. Some of those solar wind particles can travel along the field lines and they get funneled into the atmosphere around the poles, whilst the others get deflected around the Earth. At a later time, these charged particles are then shot back towards the Earth, where they enter the atmosphere, and that makes the aurora brighter and more active. The Earth's atmosphere is made up mostly of nitrogen and oxygen gas. This is just a simple representation of it. The blue balls here are oxygen molecules and the red balls are nitrogen molecules. When the solar wind particles enter the atmosphere, they can bump into those molecules and give them energy. These molecules are now energized, but they don't stay like that for long. They release the extra energy in the form of light. Different molecules will release different amounts of energy and so different colors of light. And that's why you see different colors in the Earth's aurora. Jupiter's aurora are produced in a slightly more complicated way. The planet spins once every 10 hours, which means that its magnetic field can get all twisted up. Not only that, but it has a moon called Io. Io is the most volcanic place in the whole solar system. On its surface, there are literally hundreds of active volcanoes. Every second, they release 1,000 kilograms of material out into space. Some of that material gets ionized. They lose some of their electrons. Once that happens, they feel Jupiter's magnetic field and are made to accelerate and actually go around Jupiter once every 10 hours. Some of them can make their way into Jupiter's atmosphere to give the aurora. We think that Io is actually more important at producing Jupiter's aurora than the solar wind. The Earth's aurora come in different colours. Jupiter's come in different wavebands, and they cover almost every single part of the electromagnetic spectrum. You've got them in radio, infrared, visible light, ultraviolet, and X-rays. I study Jupiter's X-ray aurora at the Marla Space Science Laboratory in Surrey. To do that, we use space telescopes like the European Space Agency's XMM Newton and also NASA's Chandra X-ray Observatory. We're lucky at the moment because we also have the Juno spacecraft orbiting around Jupiter. So we can take in situ measurements of the surroundings around Jupiter by Juno, and we can also use remote sensing data from XMM Newton and Chandra and use them together to actually find out what's going on out there. So why do we need to use two different X-ray telescopes to look at Jupiter's X-ray aurora? Well, they're good and bad at different things. Chandra has a high spatial resolution, which means it can pinpoint where each X-ray photon or particle actually leaves Jupiter. And on the bottom right here, we have an animation of the UV and the X-ray aurora. So the UV aurora is in the background, and that was taken by Hubble, the Hubble Space Telescope, and each white dot is an X-ray photon. And over time you can see how the aurora, both in UV and the X-ray, change. XMM Newton's spatial resolution is low, so it takes rubbish images, but its energy or spectral resolution is high, which means that it can measure quite accurately the energies of those X-ray photons. And just like the Earth's aurora, different molecules give off different colours of light. different molecules in Jupiter's atmosphere emit X-rays of different energies. And this is one of the ways that we can actually find out that most of Jupiter's aurora are caused by the stuff coming out of Io. So why should we care about Jupiter's aurora? Well, for one thing, they're cool, but also the more we learn about planetary aurora, the more we can apply to exoplanets. An exoplanet is a planet outside of our solar system. They orbit around other stars. We're starting to look for aurora on exoplanets. One of the things that we think is essential for life to evolve on a planet or an exoplanet is a magnetic field. They protect those living beings from radiation from their star. And so if we see aurora coming off an exoplanet, chances are that exoplanet has a magnetic field around it, which makes them more habitable. And that brings us closer to answering whether we are alone in this universe.